Hi, and welcome once again to day 18 of Just Start Programming, the Rust programming language. So, yesterday we have finally solved the issue and we've managed to show the line numbers in our mini graph programming exercise. Today we're going to go through the functional language features, closures, and iterators. And for those of you who just happened to see my video, as you can see, I'm now in day 18. It would be best if you could start from day 1, just like I did. In my first video, I would say it's not the best one, as I just started and streamed everything live with no cuts, no shortcuts. Just bear with it for the time being. Once I completed the whole book, I will edit the video and fix it. So join me once again, do it live, in one take, no shortcuts, no secrets. Well then, let's just start programming. Okay, so here we are, functional language features. Okay, let's start reading first. Rust design has taken inspiration from many existing languages and techniques, and one significant influence is functional programming. Programming in functional style often includes using functions as values by passing them in arguments, returning them from other functions, assigning them to variables for later execution, and so forth. So in this chapter, we won't debate the issue of what functional programming is or isn't, but will instead discuss some features of Rust that are similar to features in many languages often referred to as functional. So we're here to learn. We'll just go through and see. More specifically, we'll cover closures. A function-like construct can store in a variable. Iterators, a way of processing a series of elements. How to use closures and iterators to improve I/O project in chapter 12. So we need to revisit chapter 12 once again. The performance of closures and iterators. Spoiler alert, they're faster than you might think. Okay. We've already covered some other Rust features such as pattern matching and enums that are also influenced by functional style, because mastering closures and iterators is an important part of writing idiomatic fast Rust code. Idiomatic fast Rust code. We'll devote this entire chapter to them. Okay, all right. Closures. Anonymous functions that capture their environment. Rust closures are anonymous functions you can save in a variable or pass as arguments to other functions. You can create a closure in one place and then call the closure elsewhere to evaluate it in different contexts. Create a closure in one place and call the closure elsewhere to evaluate it in different contexts. Okay. Sounds like a function also. It says here, unlike functions, closures can capture values from the scope in which they are defined. We'll demonstrate how this closure feature allows for code reuse and behavior customization. Closures can capture values from the scope in which they are defined. So I think this is the main differentiating factor, because for functions, I think even for me, I was struggling a bit on the borrowing, especially the what was that, borrow and no, not traits, but lifetimes. Yeah. Capturing the event environment with closures. Okay. We'll first examine how we can use closures to capture values from the environment. They're defined in for later use. Here's the scenario. Every often our t-shirt company gives away an exclusive limited edition shirt to someone on our mailing list as promotion. People on the mailing list can optionally add their favorite color to their profile. If the person chosen for a free t-shirt has their favorite color set, they get that color shirt. If the person hasn't specified a favorite color, they get whatever color the company currently has the most of. Okay. There are many ways to implement this. For example, we're going to use an enum called shirt color that has the variants red and blue, limiting the number of colors available for simplicity. Okay. You represent the company's inventory with an inventory struct that has a field named shirts that contains a vect shirt color representing the shirt colors currently in stock. The method giveaway defined on inventory gets the optional shirt color preference of the free shirt. Winner and returns the shirt color the person will get. This setup is shown in 13-1. Okay. Derive. Okay, before we start, how should we call this? Functional language. Okay, let's create a new project. We have here this one. We know derive. Is it derive debug? Derive debug. Yes, we know. Partial EQ, copy, clone. I think this is something new. Struct. We know inventory. So enum red and blue. The shirts. A vector of shirt color. Okay. Implementation of the inventory struct. Have a function giveaway itself. User preference, which is an option. Shirt color. Red, blue. Which returns shirt color. User preference unwrap or else. This one, we don't know this. Self. Most stock. Okay, so most stocked is a function where it returns shirt color. Oh, okay, so this one will return a shirt color here. Num red 0, num blue 0. For color in self shirts. Okay. Match color. Red number plus equals 1. Num red, so is incremented. Num blue is also incremented if it matches the color. If num red is greater than num blue, shirt color is red. Okay, because here most stock is returned. Else, okay, blue is greater than red, then we return blue. Okay. Main, what do we have here? Store equals inventory, where you have shirts. So inventory is a struct, shirts. You have a vector of shirt color. Yeah, shirt color blue, shirt red, blue. So we have more blue than red. User 1 preference. Okay, so user 1 preference is red. Some red. So option will be some and none. Yeah, so that's why here some we have red. Giveaway store dot giveaway. We have giveaway. Oh, yeah, giveaway. User preference 1. User preference 1 is here. So that would be red. Print line. The user with preference user pref 1, yeah, giveaway gets. Okay, so if color is matched, increment. Okay, so in this case, if it's red, red is incremented here, and red is now 2. So it's not greater than, so it becomes blue. It becomes blue, yeah. For pref 1. When we get to pref 2, there's no preference, yeah, some and none. So user pref 2 store giveaway, so none, then it will return most stock. Most stock. So who is the most stock? Blue. Num red is not greater than blue, so blue will be returned. Okay, let's see if our analysis is correct. Let's copy this first. Okay, it compiles. Let's run the code. Yeah, so some red gets red, none gets blue. Okay, some red gets red. Why did it get red? Matches red, because there's only one red here. Matches red. Num red is from where? Num red is from this one. So does it mean, okay, red is always 0 in that case. So red becomes 1. Shirt color. Why was it red? So here blue, red, blue. Okay. Preference for 1 is red. It goes into giveaway. So giveaway will have preference red. Unwrap. Returns the contained sum value, or it computes it from closure. Okay. Because it's sum will be returned. So red will be returned. Yeah, okay, red will be returned. Yeah, It's only when it's none that it gets the most stock. Okay, red and blue 0 0 for color in self shirts. Self shirts we have 2 blue. Blue is most stock. So okay, so you have 2 for blue. Okay, because this is a loop. Blue 0 plus 1, red 0 plus 1, and blue. Okay, so it's always 2 for blue and 1 for red. And if num red, of course this is false, then it returns blue. Okay. Most stocked is only called when it's none. Okay, so let's see the explanation. Okay, the store defined in main has two blue shirts and 1 red remaining to distribute. For this limited edition promotion, we call the giveaway method for a user with a preference for a red shirt and a user without any preference. Again, this code could be implemented in many ways, and here to focus on closures, we've stuck to the concepts you've already learned, except for the body of the giveaway method that uses a closure. The giveaway method, we get the user preference as a parameter of type option, shirt color, and call the unwrap or else method on user preference. The unwrap or else method on option T is defined by the standard library. It takes one argument, a closure without any arguments, that returns T. The same type stored in some variant of option T. In this case, shirt color. If the option T is the sum variant, unwrap or else returns the value from within sum. If the option T is the non-variant, unwrap or else calls a closure and returns the value returned by the closure. We specify the closure expression vertical line or bar, self most stack as the argument to unwrap or else. This is a closure that takes no parameters itself. If the closure had parameters, they would appear between the two vertical bars. The body of the closure calls self.mostStack. We're defining the closure here and implementation of unwrap or else. Okay, so unwrap or else is implemented directly here. User preference, where's this user preference? Is an option. Okay, option. So option will have unwrap or else, but the implementation is done directly here. Okay. The body of the closure calls self most stocked. We're defining the closure here and the implementation of unwrap or else. We'll evaluate the closure later if the result is needed. Okay, so this is the output. One interesting aspect here is that we've passed a closure that calls self most stock on the current inventory instance. The standard library didn't need to know anything about the inventory or shirt color types we define, or the logic we want to use in this scenario. The closure captures an immutable reference to the self-inventory instance and passes it to the code we specify to the unwrap or else method. Functions, on the other hand, are not able to capture their environment in this way. Okay, so here, standard library didn't need to know anything about the inventory or shirt color. Okay. immutable reference to some instance and pass it with the code specifying function. Okay. Closure type inference and annotation. There are more differences between functions and closures. Closures don't usually require you to annotate the types of the parameters or return a value like fn functions do. Type annotations are required on functions because the types are part of an explicit interface exposed to your users. Defining this interface rigidly is important for ensuring that everyone agrees on what types of values a function uses and returns. It's like a contract. Closures, on the other hand, aren't used in an exposed interface like this. They're stored in variables and used without naming them and exposing them to users of our library. Okay, closures are typically short and relevant only within a narrow context rather than in an arbitrary scenario. With this limited context, the compiler can infer the types of the parameters and the return type, similar to how it's able to infer the types of most variables. There are rare cases when the compiler needs closure type annotations too. Oh. Closure type annotations, so those things exist. As with variables, we can add type annotations if we want to increase explicitness and clarity at the cost of being more verbose than is strictly necessary. Yeah, but we can also see this in the Visual Studio Code. I think there's something here like this. Yeah, but in actual code, we use VI. We don't see those things. Use store inventory, then equals inventory. That's store equal inventory. Okay. 13-2, in this example, we're defining a closure and storing it in a variable. Rather than defining the closure in the spot, we pass it as an argument, as we did in this thing 13-1. Okay, so in this case, we're storing it in expensive closure. Is it expensive? So inside you have now assign 32. It will return assign 32, and inside we have the block that performs the logic. So it will print calculating slowly, thread, sleep, duration from seconds to. Maybe it will sleep for 2 seconds. Okay. Adding optional type annotation of the parameter and return value types in a closure. Value types. Optional type annotation. This one, optional type annotation. With type annotations added, the syntax of closure looks more similar to the syntax of functions. Yes. Yeah. It looks like a function. Here we define a function that adds 1 to its parameter and a closure that has the same behavior. For comparison, we've added some spaces to line up the relevant parts. This illustrates how closure syntax is similar to function syntax, except for the use of pipes and the amount of syntax that is optional. Okay, so function add 1 is function x u32 u32 x plus 1. Okay, so this is closure. It looks like the function. And this is still closure without the type annotation. I can have this. It's not returning anything. This x plus 1. Oh, it can be done like this. I think if it's only one line, yes. Okay. The first line shows a function definition. The second line shows a fully annotated closure definition. The third line, we remove the type annotations from the closure definition. In the fourth line, we remove the brackets, which are optional because the closure body has only one expression. These are all valid definitions that will produce the same behavior when they're called. At 1, V3, at V4, lines require the closures to be evaluated to be able to compile, because the types will be inferred from their usage. Oh, so, okay. It needs to be evaluated for it to be compiled. Okay. So, yeah, let's see. Let's see this part. Let's verify. What does it mean? This one is already complaining. Consider explicit type. Okay. So if we do one, how do we use that one? So it needs to be evaluated. That total equals add 1, 2, 3 plus 1. Let's see. Cannot add integer to closure. Wait. Performs an operator. It's a closure. Okay. Okay. So how do we do it? Debug. It says it needs to be evaluated. It cannot be implemented for closure. Quick fix. Remove debug. Still doesn't work. So it means this one we need to annotate. U32. And then the other one needs to be annotated also. U32. How it can be evaluated, I don't know yet. Okay, let's continue. Closure definitions, the compiler will infer one concrete type for each of their parameters and for their return value. For instance, 13-3 shows the definition of a short closure that just returns the value it receives as parameter. Okay, this closure isn't very useful except for the purpose of this example. Note that we haven't added any type annotation to the definition because there are no type annotations. We can call the closure with any type, which we've done with the string. The first time, if we then try to call example closure with an integer, we'll get an error. So this one will have an error over here. ToString expected string found integer. Why is it expecting string? Is it because string is initially used here? Okay, let's try this one out. Okay, so 5, cannot use 5, not unless if it's string. And if we started off with that, reverse the order, then string will have an error. Example closure. Example closure. Okay, so this is the closure. If I remove the annotation, so that's how we can evaluate it. Let's see. Of course, it will complain. So comment out for now. Okay, so here let AAA equals add 1 V3. So it's like a function V3 1. Okay, by default the number is integer 32. So that's why I can see becomes integer 32. And if we let BBB add 1 V4, this one, if we, what else can we add? About we make it 2 U32. Oops, sorry. 2 U32. Will it work? It's still I32. How can we change that? Maybe, let's see, 1.0. There, to change. But you cannot add. It says here, I think you cannot add to fix it. I should be able to suggest how to fix it. No quick fixes. So I cannot do that. F64. So once you evaluate it, then the compiler would know. Okay. So in this case, the closure is I32. I comment this out, and this one will become string. See how it switches. Okay. Yeah, let's continue. Capturing references or moving ownership. Okay, so now it's all about reference and ownership once again, just like in functions. Closures can capture values from their environment in three ways, which directly map to the three ways a function can take parameter. Borrowing immutably, borrowing mutably, and taking ownership. The closure will decide which of these to use based on what the body of the function does with the captured values. Listing 13-4, we define a closure that captures an immutable reference to the vector named list because it only needs an immutable reference to print the value. Okay, so we have list vector 1, 2, 3. Okay, let only borrow, so this is a closure. Print line from closure list. Okay. Oh, it says here only borrow, so it means this line will borrow it from list. And before calling closure list, only borrows after calling closure list. So list should still be displayed. Let's copy this. That would be the output. So everything is in place. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Before defining closure list. This one from closure 1, 2, 3 list. Only borrows. It's being called. And after calling closure. Okay. Run, we have this. Next, in listing 13-5, we change the closure body so that it adds element to the list vector. The closure now captures a mutable, mutable reference. Mutable borrows mutably. Okay, push 7 borrows mutably, then it should include 1, 2, 3, 4. Let me comment out this also. Store inventory. Let's see. Okay, so here before defining closure, we have 1, 2, 3. After calling closure, this one the closure is not yet called. Yeah, but we are borrowing mutably, meaning we can change the content of vector list. So here we're borrowing it, so it can be displayed here. Okay. Note that there's no longer a print line between the definition and the call of the borrows mutably closure. Ah. No longer print line. It captures a mutable reference to list. We don't use the closure again after the closure is called. What's the difference? Here you have a print line. We don't use the closure again after the closure is called. So the mutable bar row ends between the closure definition and the closure call. An immutable bar row to print isn't allowed because no other bar rows are allowed when there's a mutable bar row. Try adding print line there to see what error messages you get. Okay, so let's try that one. Means we copy something like this, it here. So this one will have an error. Cannot borrow list as immutable because it is also borrowed as mutable. Okay, so what do we like this? Not so correct. Just guessing again. Let's adjust how to fix. No quick fixes. Borrows mutably. Is it this one? Found mutable reference. To declare a mutable variable, use mutlist. Okay, because now that is reference. That one I can remove. Let's follow the book. So it was not allowed. Mutable borrow to print isn't allowed because no other borrows are allowed when there's a mutable borrow. If you want to force closure to take ownership of the values it uses in the environment, even though the body of the closure doesn't strictly need ownership, you can use move keyword. Okay, so move keyword before a parameter list. This technique is mostly useful when passing a closure to a new thread and move the data so that it is owned by the new thread. We'll discuss threads and why you would want to use them in detail in chapter 16 when we talk about concurrency. But for now, let's briefly explore spawning a new thread using closure that needs move keyword. Okay, here. So what is this? One move. So it's a preview of programming with threads. Thread programming. Threaded programming. Okay, unlink module or unlink create thread. Quick fix. Import thread. Where's the move? Oh, move is here. Move converts any variable captured by reference or mutable reference to variables captured by the value. That sounds complex. Move closure may still implement function, even though, okay. What can we learn from here? Two variables captured by the value. Let's try running this one. Before defining closure from thread 1, 2, 3. From thread, can we copy this one since it's thread? So can we have another thread? From thread 1, this one thread 2. Oh, but why will it complain? Use of move value list. Because list has type vect at32, which does not implement a copy trait. Can I make list 2 and 4? We make this 4, 5, 6, and move from thread to list 2. Just wanted to see 2 threads. Okay. We spawn a new thread, giving the thread closure to run as argument. Okay, closure is the argument. Closure body prints out the list in 13-4. Closure only captured the list using an immutable reference because that's the okay. List here is immutable. Has a least amount of access to list needed to print it. In this example, even though the closure body still only needs an immutable reference, we need to specify that list should be moved into the closure by putting move keyword at the beginning of the closure definition. The new thread might finish before the rest of the main thread finishes, or the main thread might finish first. If the main thread maintained ownership of list, okay, but ended before the new thread did and dropped the list, the immutable reference in the thread would be invalid. Okay. Therefore, the compiler requires that list be moved to the closure given to the new thread so that the reference will be valid. Try removing move keyword using list or using list in the main thread after closure is defined to see what the compiler errors you get. Okay. So this one we can remove that one. It's irrelevant. Then here, so I just want to try once again if I keep on running it. works. What was I trying to do? So it says if the main thread finishes before the spawn thread, if we remove move, Oh, but this one straight away is complaining, so we cannot test it out. We'll see the compiler error. Okay, so it means we need to put move here. Or using list in the main thread after the closure is defined to see what compiler errors you get. Yeah, so if we do a print here again, borrow or move value, value, then here if we move this one to force closure to take ownership of list and any other reference, use the move keyword. Move list is borrowed here. Okay, so that was the suggestion of the compiler. Put move here. This one we cannot access it here. Okay, moving captured values out of closures and the FN traits. Once a closure has captured a reference or captured ownership of a value from the environment where the closure is defined, thus affecting what, if anything, is moved into the closure. The code in the body of the closure defines what happens to the references or values when the closure is evaluated later, thus affecting what, if anything, is moved out of the closure. A closure body can do any of the following: move a captured value out of the closure, mutate the captured value, neither move nor mutate the value, or capture nothing from the environment to begin with. Closure body can do any of the following: move a captured value out of the closure, mutate the captured value, neither move nor mutate the value, or capture nothing from the environment to begin with. The way a closure captures and handles values from the environment affects which traits the closure implements. And traits are how functions and structs can specify what kinds of closure they can use. Closure will automatically implement 1, 2, or 3 of these FN traits in additive fashion, depending on how the closure body handles the values. FN once applies to closures that can be called once. All closures implement at least this trait because all closures can be called. A closure that moves captured values out of its body will only implement FN once and none of the other FN traits because it can only be called once. Okay, so it can only be called once. FN mut applies to closures that don't move captured values out of their body, but that might mutate the captured values. These closures can be called more than once. So once is once, mutate is more than once. And that don't move captured values out of the body. This one moves captured values out of its body. FN applies to closure that don't move don't move captured values out of their body, and that don't mutate captured values, as well as closures that capture nothing from their environment. These closures can be called more than once without mutating their environment, which is important in cases such as calling a closure multiple times concurrently. Okay, so if you want to call closures multiple times concurrently, we use this. This one, closures can be called more than once. This one can only be called once. Okay. Let's look at the definition of the unwrap or else method on option T. We use in listing 13-1. Okay, option unwrap or else self, then F. What is this? Okay, so F is a type. This is also a type where F is of type fn1s. Fn1s is a trait. Is it a trait? Where is it? Yeah, fn traits. Fn traits. Okay, which returns T match self X. Okay, if it's some, then you get X. If it's none, then you get F. What is this? Oh, this one. Recall that T is a generic type representing the type of the value in the sum. Okay. In the sum. Variant of an option. Okay, here. That type T is also a return type. Okay, return type. That code that calls unwrap or else on an option string. For example, we'll get a string. Okay, for example, we'll get a string. Okay, option string. We'll get a string. Next, notice that the unwrap or else function has the additional generic type parameter f. Generic type parameter f. Okay. The f type is the type of the parameter named f, which the closure we provide when calling unwrap or else. That's the closure. I think it's referring to this one. So this part here becomes f. The f type is a type on the okay. The trait bound specified on the generic type f is f and once. Trait bound. Okay. Which means f must be able to be called once, take no arguments, and return a t. Okay, so it's a trait. It's called once. There's no argument, and it will return t. Let's see. So this is fn once. It takes no argument. There's no argument here, and returns t, which is option T. Shirt color. Most top. Shirt color. Okay. Okay. We can see that if option is sum, F won't be called. The option is none. F will be called once. If it's sum, F won't be called. So F won't be called. Okay, because F here is the closure. This is how you call the closure from here, from none. Okay. Note, if we want to do doesn't require capturing a value from the environment, we can use the name of a function rather than a closure. For example, we could call unwrap or else vec new on option vec value to get a new empty vector if the value is none. Compiler automatically implements whichever the fn traits is applicable for a function definition. Okay, so here we are borrowing. It doesn't require capturing a value from the environment. The name of a function rather than closure. Now let's look at the standard library method sort by key defined on slices to see how that differs from unwrap or else, and why sort by key uses fn1 instead of fn1s for the trait bound. The closure gets one argument in the form of a reference to the current item in the slice being considered and returns a value of type k that can be ordered. This function is useful when you want to sort a slice by a particular attribute of each item. Okay, listing 13-7 have a list of rectangle instances, and we use sort by key to order them by their width attribute and attribute from low to high. Okay, we have rectangle struct. We have rectangles here, width, height, width, height, width, height. Okay. Now we have sort by key. List. This is what? Okay, list is an array of rectangle struct. Okay, sort by key. R that width. Where is R coming from? Print line list. R that width. R is from here, so okay, so there's a closure here that by according to width. Sort by key. Sort by key is I think this is a function in an array. Okay, let's try this out. First, we need rectangle. And this one. Oops. Edit here. This one may comment out. Rectangle We don't have the rectangle struct. I think it got deleted. Copy, paste. Let's see. Sort by key. Sort by key. Okay, sort by key is here. You can see self mutable f and mut. So that's the fn trait used here. Fn mut can be used multiple times. And referencing t. We are borrowing t here, which returns k. K as word. So okay, so as of now we'll take it as it will sort this one. Rectangle 3, 7, 10. 3 with 3, 7, 10. So it's using with. It's using with or with sort by key. Sort by key. Okay. If the implementation of ORD for k does not implement a total order, I want to check on this now, but let's just follow what is being explained here in the book for now. I think it's too complex to digest at the moment. Okay. The reason sort by key is defined to take an fn mut. Yeah. We saw that in Visual Studio Code. Yeah, here fn mut. Is that it calls a closure multiple times, once for each item in the slice. Okay. Yeah. Because it's like we are traversing the array. The closure doesn't capture, mutate, or move out anything from its environment, so it meets the trait bound requirements. In contrast, in listing 13-8 shows an example of a closure that implements just the fn once trait because it moves a value out of the environment. The compiler won't let us use this closure with sort by key. Where's the fn once here? Sort operations push or with. Let's copy this one. Push value. Okay, so if we check this, what will happen? It's still fn mut here. No. Oh, where's the fn once? How do we know if it's fn once? a captured variable in an fnmat closure. Move occurs because value has type string which does not implement the copy. Sort operations. Where's sort operations? Here. Comment this out, it will be just like we're not using sort operations anymore. Type annotations needed for vec. Because it's unknown. Okay. Put rectangle here. Can we do 11, 20? No. Missing structure field. So this one is like just like this one eventually. But if we put in a value, push value is a string. Value is a string. Set operations that push value. Value is a string. But why did we do string here? That value equals, I'll put rectangle instead. One. Still complaining. Cannot move out of value a captured variable in fnmat rectangle which does not implement the copy. Rectangle, if rectangle implemented clone, you could clone the value. Okay. I'm just curious, how exactly do we implement the copy for rectangle? Let's see. npm rectangle. Did it give some hints? Copy trait. So copy trait. How do we implement trait again? Copy. Oops. Copy. No. What are traits again? Summary 4. Summary 4. Okay. Copy 4. Okay. Required in copy. Clone is not implemented for rectangle. Let's go to implementations. And clone. What is the signature? It would be nice if it will autocomplete. Consider annotating rectangle with derived clone. Derived clone. Sharp derived clone. Can we add clone here? Clone. And what happened to, oh, no value, we don't have error anymore. Okay, let's see. 3, 7, 10. That's what exactly happened there. 3, 7, 10. Push. Sort operations. Push value. Sort. Print list. Okay, sort operations was just added here, but of course it doesn't change the list. Does it change the list? No, it didn't seem to change the list. I don't know what's the purpose of putting it here. Yeah, I think it's just to illustrate attempting to use fn1's closure with sort key. Okay, because fn1's is closure that can be called once. A closure that moves captured values out of its body will only implement fn1's and none of the other fn traits because it can only be called once. Okay, the explanation is here. Cause a closure when sorting list. Sort by key. Cause a closure when sorting list. Okay, sorting list. This code attempts to do this by counting by pushing value string from the closure environment into the sort operations vector. The closure captures the value and then moves value. Okay. Moves value out of the closure by transferring ownership of value to the sort operations. It's inside the closure by putting value here. Ownership is through sort operations vector. This closure can be called once. Trying to call it a second time wouldn't work because value would no longer be in the environment to be pushed into sort operations again. Okay, because it's the value is now owned by sort operations. Yeah. Okay. Moves value out of the closure. Yeah, because we are putting it here. So it's owned by sort operations. But if we put a reference, it won't be owned by sort operations. Let me comment this out. Let me put back string. So yeah, so this is not allowed. Or because I forced it to be string rectangle. I'll remove rectangle. Type string, which does not implement a copy. Here, it's not borrowed anymore. Does it mean that this will be fn mat? So it worked. Just that if you, this one is to illustrate that the ownership is here, sort operations. So the next time value is no longer there. The next time it will iterate. Okay, so that is clear. So we get this error, the value can be moved because the closure must implement fn mat. Closure must implement fn mat. The error points to the line value. Okay, so I'm just curious. What do we have here? The closure in listing 13-9 works with sort by key because it is only capturing a mutable reference to num sort operations. Okay, so it's a mutable reference. Mutable reference. How do we know it's a mutable reference? It's mutable. Let's try this out. Mutable reference, mutable, yeah, it's mutable. Because this one has a function. Num sort operations. So it was saying that that one will work. Yeah. Sorted in 6 operations. By 6. Sort by key. Num sort operations. Okay. Of course, num sort operations is not relevant here. It's just to illustrate that inside the closure, this one, since this is implementing fnmut, this is fine. I think it's a difficult topic. So tomorrow, what I will do, I'll go through this once again as a review before proceeding to the next topic, so that we won't forget the concept. Day 18, but I think I'm starting to forget some of the topics here as well. So maybe what we can do tomorrow is to scan some of the key topics here, and then we review this one, closures, and then we proceed with the next topic, which is items with iterators. Okay, all right. So let's end here. Thank you so much for joining me, and I hope you learned something as well. But before that, let me thank those who supported me as well.